Hi, I'm Zachary Stever, PhD candidate in operations research at the University of Buffalo and member of the Optimator Lab. This video describes research I'm conducting on how to identify similarities among mixed integer programs, or MIPs. More specifically, we've developed a comparison approach based on images which represent an MIP's mathematical structure. Before we get into the details of this approach, though, we should discuss the motivations for this project. As operations researchers, we make comparisons in many facets of our work. To demonstrate how difficult our problems are to solve, we often compare them to problems with a known computational complexity. For example, a problem that is NP-complete. There are also many different ontologies designed to classify models in a given field. Kendall's MM1 style notation for queuing models is a familiar example of this. This type of comparison is often used to inform a literature search. In fact, we devote an entire section to related literature in almost every paper we publish. In this section, we use comparison to demonstrate what differentiates our work from the existing literature in a given research area. So, if all of this exists, what is the value of developing a new comparison approach? Well, comparisons based on computational complexity are too broad to guarantee that two problems in the same class will benefit from the same modeling techniques or solution approaches. Meanwhile, comparisons based on a model ontology are siloed based on a specific research area. In other words, they don't allow for connections to be made between problems with different applications, even if those problems are mathematically similar. All of this left me asking myself, is there another way to identify similarity among MIPs? Here you can see the general formulation for a mixed integer program. In our comparison approach, we focus on the structure of the A matrix. We call this a constraint coefficient matrix, or CCM. We represent CCM structure using grayscale digital images. Computers store grayscale images as matrices of pixel values ranging from 0 to 255, where zeros are black, 255s are white, and values in between are shades of gray. By taking the absolute value of a CCM and normalizing its entries, we can render CCMs as images. When you repeat this process for MIPs from different application areas, many unique and interesting structures appear. But how do we use these images to compare MIPs? The methodology for making these comparisons is detailed in our companion paper, which will be linked in the description. In general, however, this process can be broken down into 3 steps. The first step is to generate images. To do this, we use the software called GCG, which stands for Generalized Column Generation. This software reorders the rows and columns of a CCM to make structures more readily apparent. Then, we use the command line graphing tool GNUplot to render the images for these reordered CCMs. Next, we use deep learning techniques to encode these images into feature vectors. Specifically, we use an autoencoder, which is a form of neural network which learns latent features from input images and uses those features to reconstruct the inputs as best it can. Once the autoencoder has been sufficiently trained, that is, it can reconstruct the input images with a high degree of accuracy, the innermost layer can be extracted for use as a feature vector. Finally, we measure the similarity between two images as the Euclidean distance between their feature vectors. We refer to this value as the image-based structural similarity, or ISS. A low ISS value implies a high degree of structural similarity between two images. In order to test this methodology, we needed a collection of MIP instances. For this, we relied on the 6th edition of the Mixed Integer Programming Library, or MIPLIB 2017. MIPLIB 2017 contains over 1,000 MIP instances. For each instance, they provide descriptive information, such as the submitting author. Each instance can also be downloaded in the MPS file format and loaded into your solver of choice. Of note, a subset of the instances in MIPLIB 2017 have been assigned to a model group. Instances in the same model group come from either the same model or variations of a model from a common submitting author. We represent these model groups by stacking the CCM images for each of the component instances. We refer to the resulting images as model group composites, or MGC images. Just as CCM images can be used to compare MIP instances, MGC images can be used to compare MIP models. We applied our image-based comparison approach to 992 instances and 238 model groups from MIPLIB 2017. We refer to our analysis as the MIPLIB image comparison, or the MIC. All of our results are housed on a companion website, mic.optimatorlab.org. So what types of things did we learn from the MIC? Well, let me give you an example. Consider the model group called cryptanalysis, which comes from the field of cryptography. The third most similar MGC image to cryptanalysis, according to the ISS metric, comes from the model group called Seaway Sun. Interestingly, this model group also comes from the field of cryptography. Okay, so image-based comparison can relate models from the same field. That's good, but what about the first and second most similar MGC images to cryptanalysis? To understand how these models might be related, we have to look at their problem descriptions more closely. First, let's consider the cryptographic problem, as described by the Seaway Sun model group. The problem here is to decipher an encrypted binary string. To do so, the encrypted string is multiplied by a binary cipher matrix. Ones and zeros in the cipher matrix act as a series of yes and not gates. Each incorrect bit in the output string is considered a conflict. The goal is to develop a cipher matrix which deciphers an encrypted input string with the minimum number of conflicts. Now, let's consider the Huefner model group, which was rated most similar to the cryptanalysis model group according to the ISS metric. The problem considered here is the balanced subgraph problem. Given an m by n input graph, the problem is to identify a two-coloring which is color balanced. However, every edge in the graph has also been labeled with either an equals or a not equals sign. Vertex color assignments are represented in a 1 by n binary vector. Similarly, edge labels can be represented in an n by n binary matrix. The optimal two-coloring is the one which minimizes the number of failed edge assertions. Finally, let's consider the Lecht-Sked model group, the second most similar model group to cryptanalysis according to the ISS metric. The problem considered here is the university timetabling problem. At this point, you might be noticing a pattern. Here, an n by n conflict matrix marks which courses are in conflict with one another. For example, those that require a common professor. Course assignments are labeled in a 1 by n vector, and the goal is to identify a timetable which minimizes the total number of conflicts. Although these problems come from very different fields, they appear to be solving very similar mathematical problems, namely, minimize the number of conflicts between a 1 by n vector and an n by n matrix. Image-based comparison is agnostic to problem application and has identified these relationships based solely on the structure of these problems' constraint coefficient matrices. There are so many interesting results like this from the MIC, and the longer you look, the more you'll find. Here are some helpful hints on how to navigate our website so that you can explore on your own. On the Instances page, you can find the list of all 992 instances from MIPLIB 2017 which were considered in the MIC. For each instance, we present the raw and decomposed CCM images, which were generated before and after the rows and columns were rearranged by GCG, respectively. At the top of this page, you can also find the lists of instances from MIPLIB 2017 which were not included in the MIC, along with discussions on why they were left out. Click on any name to see the analysis for that instance. Up top, you'll see the raw and decomposed CCM images, as well as the composite of the MIC's top 5 most similar instances and the MIPLIB's top 5 most similar instances, as well as the model group composite image which that instance belongs to, if there is any. You can also view all the backgrounds as white if that's easier on your eyes. Here you can see the top 5 most similar instances according to the MIC. Their decomposed CCM images are in the top row, and their raw images are in the bottom row. Their rank and ISS values according to the MIC are reported in between. Here are the top 5 most similar instances according to the MIPLIB. Their rank and ISS values according to the MIC are also provided. Descriptive information and MIC statistics are provided for all of these instances in an instance summary table. If this instance was assigned by MIPLIB to a model group, that information will be provided here. Next, the 5 most similar model group composite images to this instance's CCM image are provided. These model groups are described in a model summary table like the instance summary table above. The 238 model groups from MIPLIB 2017, which were considered in our analysis, are listed on the Model Groups page. Click on any model name to view the corresponding analysis. Once again, you can view these images with either white or black backgrounds, depending on what's easier for you to see. In the top row, you'll find the CCM images for every instance which was assigned by MIPLIB to that model group. Below that, you'll find the 5 most similar model group composite images according to the MIC. Their ranks and ISS values are also provided. Once again, these models are detailed in a summary table below. Finally, visit the About page for links to our paper, citation information, and links to the personal web pages for all the MIC team members. Hey look, there I am! On behalf of myself and the other members of our research team, Drs. Chase Murray, Junsong Yuan, and Mark Carwin, I want to thank you so much for taking the time to watch this video. And please, feel free to contact us with any questions you might have. Goodbye for now.